Start presenting. Okay. So let's get started. So what we're going to do today is we're going to look at programming with lists. This is going to start off looking very similar to how we programmed with lists in OCaml, but pretty soon it will get a little bit weird, right? Because we are doing this declarative reasoning. Everything starts becoming a bit strange. So have an open mind, right? So don't try to fit all of the concepts with what you know. I think that's a good position to start off. But soon enough, it will start looking very different from what you've sort of seen previously. And that's a good thing, right? So we'll sort of see what that brings in as we go through the lecture. So in the last class, we looked at logic puzzles. And today we are going to look at lists. We are also going to look at a few different concepts as we go through the lecture. We are going to look at how we do arithmetic in Prolog. How we do, so there is this optimization called last call optimization, which is analogous to the tail call optimization that we saw in OCaml. And then we will also have a look at Prolog's way of producing multiple results, which is backtracking and choice points. So we will cover all of this in this lecture. I'm hoping that I can finish this lecture off in 2 days, right? So 2 classes. We'll see how it goes. So we had a look at this zebra puzzle in the last class, and we had a street configuration that had 5 houses, right? And we said, okay, we will use a 5 tuple, where we said the street is a function that has arity of 5, and we had 5 houses, h1 to h5, right? And if you sort of think about it, if I change the problem to have, say, 6 houses, you would have to change the entire problem structure, right? Instead of having 5 as a fixed number, you would have to talk about 6. If I change to 7, then you need to change the problem again. So what you need is some data structure where the data structure itself is parametric over the length of the number of elements in the list, right? So what you need is really lists. And lists is what we are going to look at today. So first thing we are going to look at is the syntax for list. In Prolog, list is notated with open braces, close braces, but have commas between the elements. So this is a list which has 4 elements, 1, 2, 3, 4. Empty list is this empty list, just like OCaml, with open square braces and closed square braces. And list pattern matching is matched this way, where you have an open square braces, you have a head element, right? And then you have a vertical bar, and then the tail list. So this pattern matches, this unifies with a list which has at least 1 element, right? And the first element is going to be unified with this variable h, and the tail of the list is going to be unified with t, right? So h is a list element and t is a list, the tail of the list. You can also match multiple elements. Rather than just having to match one, you can match multiple elements. You can match something like 1, 2, 3 and some arbitrary tail. So this term unifies with any list that has 1, 2, 3 and any suffix at all. The suffix could be empty list, suffix could be any other list. So this term unifies with any list whose prefix is 1, 2, 3. Okay, so that's that is a syntax for lists. So here are a few questions to see whether we've understood the list syntax. So which of these terms unify? So you can type your answers in the box chat window. So does 1, 2, the list 1, 2 unify with a list with head and this tail, which is 2, constant list 2. So equality is unification, in Prolog, right? When I write this term equals that term, I am asking Prolog whether these two terms unify. Is one true or false? Does the term unify? Think. Okay. Various different answers. So the answer is true, right? It's true because we can write this list in the same way as I just told you just earlier, right? So you can write it in this form. You can also write it in this form. Both are the same. So what we're doing here is we are trying to say, I have a list with 1 and 2. I'm going to unify this with H and tail is just a 2, right? It does unify where H is just going to be equal to 1. And tail is the list 2. So that is going to be list 2. So these two terms do unify. And H will be, the value of H will be 1. Okay, the answer is true here. Okay, so that's okay. What about the second one? Does that unify at all? So this is list 1, 2. This is some pattern which is head is 1 and the tail is just 2. Okay, good. False is the answer because this has to be a list, right? But this is an element. It is not a list. So these two terms do not unify. What about the third one? Does the third one unify? Recall that you can have multiple patterns here, right? So with commas. True is correct, right? So X unifies with 1, Y unifies with 2, and there is an empty list. So empty list is the tail, and that unifies with this empty list. What about the last one? Is that true or false? False is the answer, right? As I mentioned, when you have a pattern like this, H has to be an element, right? It cannot be, it has to at least, this pattern matches a list which has at least one element. Here, 1, 2 is the list, right? I'm saying tail is 1, 2. That you cannot have any element here. So this pattern unifies with any list whose suffix is, sorry, any list which has 3 elements, right? Whose suffix is 1, 2. But this list has 2 elements. This has to match with some element. We don't have such an element. So this will be, this will not unify. So there is a question, what will be x comma y in 3? So x will be 1, right? And y will be 2. And that's the unification result. Okay, so sir, how does underscore unify? Underscore unifies with something, right? So here, if you sort of look at it, this is the way you sort of look at this is a list, right? Which has the tail 1, 2, and underscore you have to unify with something. And the idea here is when you have a list pattern, this is one or more elements. You must have a comma here. You don't have a comma here. So it matches with one element exactly. So this matches with exactly one element that is not there because our list itself has only 2 elements. So this pattern will unify with say 0, 1, 2. Why don't we actually play around with the terminal just to show these things working. Oops. You still see the window? I can't see it here. Okay, you do see it, but it's a bit small. Is it? Make it bigger. Yeah. Yeah, exactly. So all of these questions, right? These are valid Prolog terms. So you can, let me see how I can get to the other one. I need to take it off full screen. Okay, so these questions that I asked here, right? These are all valid Prolog terms. So I can actually ask that here. So let me copy this, right? And then paste it here. Let me clear the screen. You can read it, right? It's big enough for you. Is it? Yeah, okay, good. So you can type this and ask whether it unifies. What we are asking Prolog is we are asking a query that we are saying just solve for unification. This will come back with false, right? Because we need an extra element. If I do this, this will come back with true. If I add an x here, this unifies and solves for x as well. So it says x must be 0 here. And similarly for the previous one, just to make sure we understand it, right? So this is unifying x with 1, y with 2, and in this list, there is always a suffix of empty list, right? And that is what is unifying with the tail here. So it prints x equals 1, y equals 2. So you can ask these questions in Prolog. So these are not, these are actually programmable things. Okay, so that's good. So hopefully we've had some idea of the unification. We'll see more later. So we'll continue looking at this for the next 2 lectures. Okay, good. So yeah, so this right-hand side term will unify with any list which has this structure where x is a variable, right? So you can have any x. That doesn't unify. So there is a question, which is, let me see, let me copy paste this, right? So the question is this: does this unify? Oh, sorry, I don't think I copied it. Copy. Actually, it's just 3. So this doesn't unify because what the problem is that we are saying this particular list has exactly 2 elements, right? So yeah, okay. So here is there is another question which is so it unifies, right? What does each one unify? You can just write head and tail. So head is 1 and tail is 2,3. No, it can't, right? So there is a question. So the point is underscore does not unify with comma is what I think you are asking. Yeah, underscore does not unify with something that has like this is not valid, but it doesn't unify. So underscore unifies with a single element. So you cannot pattern match with 1, 2 is what I think that's all of the questions are sort of tending towards that. So when we write something like underscore or underscore, there's only one unification. I think this is the best example, right? So when we write underscore or underscore, that's one. Maybe we can do underscore underscore, right? Because the right hand side is a tail, right? Tail. So this position is a tail position, and tail is a list. So we unify with the tail of the list. But here, the thing that appears here is either a single element, and comma is a special case, right? I can do this. So x comma y and t, if I do this, right? This unifies with 1, this unifies with 2, and the tail unifies with singleton list 3. But if I just write x comma tail, x is unified with just the single element 1. Does that answer your question? Okay. So the thing is, when you write, variables never unify with something that has a comma because the comma is a special syntax, right? When you read this 1, 2, 3, yeah, precisely. So there is a question which says underscore takes different values depending on positions. Underscore is like a catch-all thing, right? And you have to sort of think about that as based on the position, what can unify, right? So you can think of underscore as underscore 1, underscore 2. Those are 2 different underscore values. And I'm unifying that with 2 different things. So when I write underscore underscore, I'm not say, all I'm saying is I don't care about the value that I don't care about the variable value. This is just equivalent to doing something like h and t, right? Where Prolog prints h and t values. Okay, so that's the idea there. Any other questions on this? Okay. So okay, so I think that gives us enough of a background to ask more questions about lists. So let's switch back to the window if I can find it. I did find it. Okay. So, so that's unification. So let's start writing small programs, recursive programs that answer questions about lists, right? So the way to imagine this is we are describing some set of facts and rules, and we are asking queries about those, right? So I'm going to define a set of clauses for finding the last element of the list. And the way to read this is these are declarative statements, right? These are not, although they look very similar to how you would write recursive programs in OCaml, sort of look at them as just facts. The first one that is saying is, if you give me a singleton list with element h, the last of that list is going to be h, right? And if you give me a list with some head that I don't care about and some tail, the last of that is going to be v if the last of the tail is going to be v, right? So so those are the two cases for the list, and they match the ground case, right? The base case and the recursive case. Okay, now you can ask, let me load these facts up. So we've loaded this into the database. So it says added two clauses. If you run it again, you won't have any output here because these clauses are the same thing as what you've loaded earlier. So Jupyter Notebook has this facility where it ignores repeated facts that you previously added. Yes, so an empty list with a singleton list. So there is a question. A singleton list with element h is equivalent to the pattern, this pattern. Yes, that is true. We'll see how that actually works out. You are hitting upon an interesting point. So let's see how that plays out. So now let's ask Prolog for the answer for last of 1, 2. So of course the answer is 2, right? The interesting question is how Prolog came about solving this, right? And for that, what we're going to do is we are going to actually try to trace this example by hand. Let's, I'm going to try to connect my iPad and then show this in practice. Let's see. Screen mirroring. 5858. Okay. So can you see this screen? Let me see. I am in a very Yes. Okay. Good. I made lots of things full screen, so I've been playing around with. Okay, so let's. So what we wanted to see is how do we solve for last 1, 2? Let me take it off full screen so that I can actually switch back and forth. Okay, so we are going to solve. Okay, fine. So we are going to ask how does Prolog answer the question of last of 1, 2 x, right? And we had seen some of this earlier. So what Prolog is going to do is SLD resolution, right? So it's going to look at the rules that you've written in the order in which they are presented and try to find a matching, a unifying rule, right? And then tries to go ahead and solve it. So the first rule that it picks up is last of h, right? That's the first fact that we have. So what Prolog is going to do is say, I'm going to try to unify this, see whether this is satisfiable. Okay. So one thing we will do in this process of writing down things is we will keep renaming variables all the time so that we don't get confused between variables that appear in different selections. This is precisely what Prolog also does internally. So what I'm going to do is I'm going to write it as h1, h1. right? And what I'm writing down here is basically Prolog's evaluation, right? So I'm just writing down the Prolog search tree. So let's see. So the question is, do these terms unify? So of course the variables unify, right? This variable h1 unifies with x, but now we have to ask whether this term unifies with this term here. So that means does h1 unify with 1 comma 2? Does this unify? Yes or no? No, right? It doesn't unify because this is a singleton list. This is a list with two elements, so it does not unify. And what Prolog does is, okay, that doesn't unify, I'm going to come back. And we have a second option, right? Uh, we tried this, that doesn't work. Let's try the rule, right? So let's write down the rule. The rule says last of underscore T2. I'm just renaming it. I'm going to not mention it again, but I'll just keep renaming variables. Last of T2, comma V2. Okay.
Yeah. We can't see your screen.
Oh, sorry. Yeah, this is going to be a tricky. Thanks for saying this. So, if I do something stupid like this, just call me out, right? Let's make sure we understand. We can actually see the screen. Okay, so what I've done is I just renamed the variables so that these are visible. So now we are going to try to ask whether the head of the rule, right? Head unifies with the goal that we have. This is the goal that we are trying to do. Does that unify? Yes, it does. And what it's going to do is this underscore is going to unify with 1, as we saw earlier, right? And T2 is going to unify with the singleton list 2. And V2 is a variable, so that unifies with X, right? So, okay, so now we found something that unifies the head. So the Prolog resolution, just like we saw in logical foundations, what it's going to do is, in order to, for this to be true, the right hand side must be true. All of the body of the rule must be true. And we have a single goal there. So let's transfer all the unification information over there. So we know T2 is the singleton list 2, and V2 is X, right? So now what do? We say, okay, this is the new goal that we want to satisfy. Okay, so what do we do about this goal? Okay, now because we have a new goal, we have to start from the beginning again. So let's go back to the program. Oh, okay, so we see this last of a singleton list is H. Let's see whether that unifies. So this goes off, right? And says, okay, last of H3 is H3. And now we are unifying singleton list H3 with singleton list 2. Oops. Yeah, okay. Thanks, Naman. Yeah, so we are trying to unify this. And what happens is, oh, this one perfectly unifies, right? And because we have a unification here, we know that we can have the value H3 for 2. And this becomes 2. Okay. This is actually satisfied. This goes through. This is a fact. So there is no right-hand side body for us to follow. So what happens is this comes down. Prolog says, okay, I'm going to come down with the result. H3 is 2. And the thing that I forgot to write down here is this V2 is going to be unified with H3, right? This H3 here is the V2 here. So I went, this should be V2. V2, right? So this fact comes down, and what do we know? We know that this is equal to now 2, right? Because we are just lowering down the unification result, and we just go backwards along the tree. So this goes back. So X is now 2, and that's the head of the rule. So we go down now, and X is 2. Okay, so we solve for X, and now what Prolog says is X equals 2. So that's precisely what Prolog does when it computes the result of this query. So this is the Prolog search tree, right? We'll keep looking at these search trees. It turns out that in order to understand how Prolog programs, the results of the Prolog programs, you have to actually know about the search tree. It's a bit backwards, but once you do this for a little while, right, you'll catch hold of what is happening. Okay. Any questions on this? How I did this unification? Nothing so far. Okay. We'll keep looking at more and more examples. Okay. So let's switch back now. Okay. So that's how Prolog actually produced the result x equals 2. Okay. So this is what I did. Trace example by hand. So okay. So with that information, right? Here is a question. So that's the program that I had written. And what if I ask for the last of an empty list? I'm querying last empty list X. What will Prolog return? Good. False, right? Exactly. So what Prolog does is, oh, this is the goal. Let me try to unify it with one of the clauses, either the fact or the head of the rule. This is matching with a singleton list. This also matches with a list that has at least one element, right? But this has 0 elements, so Prolog comes back and says false. So that is the reason why Prolog will say false. So yeah, so let's now trace the same program in the Prolog interpreter, just so that we are sure that we know what is happening. Okay, so let me switch to the Prolog interpreter. I think I need to come out of full screen here. Okay, and then yeah, okay. The program is this. I'm going to copy paste this. So let me actually start a new interpreter. So the way you type the program is you do user, right? That enters into this mode where you can type out the clauses. I've copy pasted the two clauses, and when you are finished entering the input, you just press Control D, and that loads the two clauses, right? Now what we are going to do is to trace the result of query, trace the query last 1 to x. So let me turn on tracing. That turns on tracing, right? And I'm going to ask last of 1, 2 x. So the first thing that Prolog does is it actually renames this variable as well. It says, okay, I'm going to rename this variable x to some other variable, and then it's going to proceed. So the thing that Prolog doesn't actually show explicitly is that Prolog first would have tried to take this goal and try to match it with this fact, right? And that doesn't unify. And so it says, okay, I give up and move on to the next clause and match with this head of the rule. And that unifies, and then it goes ahead and says, now the recursive call is going to be on the tail, right? That is what Prolog is directly showing you. So it is sort of implicitly doing this. It's not showing this in trace, but that is what is happening internally, right? When you see this call here, that corresponds to the body of the rule in the second clause. So if you proceed, so this one directly goes ahead and unifies, right? We were here, and that unifies with the fact. The last of a singleton list with 2 is going to be 2. So that variable got unified to 2. So that's why it was successful and it exited from that call number 9, right? And now this comes back out of here, right? And then says, okay, I've satisfied this. 1, 2 is 2. If I step here, Prolog says x equals 2, and then stops, right? So this is what we expected. Okay, that's fine. But Prolog says Prolog doesn't give us the query prompt now, right? It is sort of stopped here. Prolog says that's the first result. I think there are further results, is what Prolog is saying, by not returning to the query prompt. Why is this the case? This is the case because of what Nishchit had observed earlier, right? He had asked a question which is, does singleton list is equivalent to unifying with the second pattern, which is some head and empty list tail? The observation here is that this particular goal, right, happened to unify with the first fact, right? It unified, we got an answer, we are all happy, but it also unifies with the second fact, right? Where the head is going to be some element, the tail is going to be some tail, right? I don't care about it. But the observation is this particular goal also unifies with this head. So that is what Prolog is saying. Okay, I found an answer here, but there is another choice as well, and I haven't explored that choice yet. So what Prolog does is that if there are multiple further options that you can explore, it stops and then says, okay, if you want more answers, press semicolon. So when I press semicolon, right, it goes back and says, okay, I was here, right? And then what I did was I went ahead and unified with this. I gave you an answer, but there is a second clause that I haven't explored yet. Let me try to explore it, is what Prolog is saying here. That is why it says redo at level 9, right? It says last, it rolled back all of the unifications, and it is at a point where it is going to explore the second one, right? So last of underscore 9780, the same variable, right? It forgot. Yeah, so Satak is looking ahead, but that is precisely what is going to happen, right? So it's going to try to unify with this head, right? And it does unify, right? Underscore can be unified with 2, tail can be unified with the empty list. So if I creep, the recursive call is precisely that, right? Tail can be unified with the empty list. So tail is empty list, and V is going to be the same variable. And you're going to continue, Prolog is going to continue, try to satisfy this, as we had just seen in the question quiz earlier, right? This is going to return false. So if you keep creeping, this particular goal does not have a solution, so that fails. You creep again, that also fails. This also fails, and Prolog says false, right? So what Prolog did here is explore the tree, the program tree exhaustively, right? It said the first result is 2, and for the further result it is false, right? So this is Prolog way of going completely through. The Jupyter notebook is not printing the false, right? It is just printing the results. If there are multiple results, it will print all of the multiple results. But if you actually run it in SWIPL, the interpreter, it will give you options, right? X equals 2, and the second option is going to be false. This is a bit strange. It's strange because it is the computation model is deduction, right? It said if I forget the first option happened, right? If I consider that has failed, right? That is why it says redo here. If I imagine that to be a failure, there are further options. Let me explore it, and for the further option, it is false, right? So you will see this over and over again with Prolog. So Prolog will give an answer and then end with false. We'll come back to this. This closely ties to this idea of choice points. It gets much more interesting when you want to get further results, like more than one result. Here we have only one result, so it is sort of strange to produce false here, but it makes sense later. Anyway, questions on this? Okay, if there are no questions, let me proceed and we'll see a little bit more. Okay, so Okay, we computed the last one. Let us now do the length of the list. Okay, so we are going to write a simple program that is going to take a list and compute the length. But in order to compute the length, we need arithmetic, right? We need to take numbers and add and subtract and so on. Arithmetic is quite natural in imperative and functional paradigms. We just say, oh, that's arithmetic, we know how to do it. But in Prolog, it's quite strange, right? Because our computation is deduction here. All Prolog is doing when it's computing is it is doing logical deduction, and this arithmetic notion is um, sort of you have to sort of fit that arithmetic notion into this computation model, which is deduction, right? So arithmetic is sort of quite special. We won't look at the details of how you can encode arithmetic in logic, but you can certainly do it, and that is how Prolog convinces itself that that is sane to do. But we are not going to look at it in detail. But just keep in mind that arithmetic is quite special in Prolog. Okay, so okay, with that, as we had looked at earlier, right? This equality symbol, we have used it up for unification. So whenever we write T1 equals T2, equality is unification. So arithmetic equality in Prolog is not equal to unification. So we cannot use equal to symbol. We have to use something else. Just to show you how this works, when I query A equals 1 plus 2, I am not saying compute 1 plus 2 and then store that result in A. That would be an imperative way of thinking. What I'm saying here is, does the term A unify with the term 1 plus 2? Right? And Prolog says, okay, that is true. It does unify. And it looks at the abstract syntax of this term, which it happens to always represent with this prefix notation, right? It just says, okay, plus is a function, right? Function symbol that has two, arity 2. And the arguments are 1, 2. That is what we are constructing here. And that compound term does unify with the variable A. And it simply says, okay, A is that variable. So when we write A equals 1 plus 2, all we are doing is unification, right? And what do you think? So if I say plus is some function symbol, right? What do you think will be the result of 1 plus 2 equals 3? Recall that equality is just unification and plus is just a function symbol, right? We are not doing arithmetic yet. False, right? False is the answer. We are not doing arithmetic, so true is not the answer. So all it says is, oh, this compound term, right? Does that unify with the constant 3? Atom 3, it does not unify. So just go back to the unification rules, right? Compound terms unify with compound terms which have the same top function symbol and the same arity, and the arguments recursively unify. This is a compound term. This is an atom, right? 3 is just an atom as far as Prolog is concerned. So that is not unified. In fact, you can add anything, because plus is just a function symbol. You can say A equals money plus power, and that just unifies happily and says, so plus this, what you've done is you've written a function, a compound term whose function symbol is plus and has arity 2, and the arguments themselves are two atoms, money and power. So this is not, so you can easily get confused here, right? Equality is not used for arithmetic. Equality is for unification. So what do we do for arithmetic then? So we have this operator called is, right? Is is a special operator. Is operator tells Prolog to evaluate the right hand side, right hand expression numerically and unify with the left. So when you have is and something on the right hand side, Prolog will try to do the usual arithmetic on the right hand side and then unify the result with the left hand side, right? So here what I'm doing is I'm saying x is 1, right? So 1 is just it is going to take this and evaluate it arithmetically. There is no further arithmetic to do. It's just 1. So and then unify x with 1. So x is unified with 1, right? and you take that and apply it to the right, the next goal. So x is 1 here, right? And now we write a as x plus 2, which in turn translates to a is 1 plus 2. Because we have an s operator here, we are going to do 1 plus 2 is 3. And the result 3 is unified with a, right? So a will be 3 here. So x will be 1, a is 3. The key point is the s, right? When you have s, you look at the right hand side, you evaluate the right hand side arithmetically, numerically, right? And then you unify the result of this evaluation with the left hand side term. That is all what Prolog is doing. So if I write something like a is money plus power, the rule is that on the right hand side, it has to be a numeric term that it evaluates. This is not a numeric term, right? So Prolog is going to complain. It produces very strange output. But anyway, so I think if you do it in the FWIPL thing, it might give you a better result. Let's see. Yeah, it produces something even worse, right? So yeah, I don't even want to explain any of this because I don't know. But if you do this, it produces something that is says money is not a function, but the error reporting is not one of the strong points of Prolog, right? Let's just leave it at that. But the thing that is failing is that this thing is not a numeric term, is what we are essentially saying. Right? Forget about the error. We won't dig in too deeply into any of this. So there is a question: how do we define a function like plus in Prolog? You just write it out. You just define. Yeah. So there is no definition, right? In Prolog, we can't. It's not like we can. Yeah. So it's not like we predefine function and then use it. So if I want to use something, I think there are like allowed tokens. So you can write 4-3. Okay. So a equals 4-3. So this is how we are not defining functions here. We are just writing out. So just like you can do this, right? There are some allowed operators that you can use. I think let me try something which I haven't tried previously. Maybe this works. Yeah, that also works. So we are not like in Prolog, we don't define functions and then use it, right? We just happen to use it. And if it is one of the allowed terms, we can happily use it. So I'm using hash. That is special, right? When you have an S, it knows about certain operators. I'll come to that. That is what I have in the next slide, I think. So yeah, okay. I'll come back to that. But another restriction about the is operator is that when you actually come to the is operator, the right hand side must be a ground term. So you shouldn't have any variables. Prolog doesn't do algebra, right? So here is a query where I say a is b plus 2, right? Prolog looks at the right hand side and it says, okay, I don't know what b is. I can't proceed. So Prolog doesn't give you an answer. And for the same reason, this is not going to be satisfied by Prolog. I'm saying 3 is b plus 2. We know that b is 1 here. If b is 1, this will be unified. But Prolog doesn't do algebra, right? It's not a solver underneath. So when you do b plus 2, when you do s, it is looking at b plus 2 term. It doesn't know anything about b. So it says, I don't know anything about b, I can't proceed. So it says instantiation error, right? And that's and it basically says, okay, I don't know what to call this thing. But if you do b is 1 and then 3 is b plus 2, it works out, right? B is 1, so b equals 1, and it applies that fact here. So this is turned into 1 plus 2. 1 plus 2 can be numerically evaluated. And all Prolog does is, after it numerically evaluates, it is going to do unification of the terms. So it is going to unify 3 with 3. So both are ground terms, both are atoms, and these atoms unify, right? And for this reason, 4 is 3 plus 2 will not unify, and it gives false. Because this is 3, right? And this is 4. these atoms are not the same, so they don't unify. Okay, let me put it back to what it was. Any questions on this? Actually, let me proceed, right? We'll proceed and then I'll stop for questions. So what is the result of A is this form times 3 plus 1 comma 2. Evaluate it numerically, right? That is 9, right? Okay. So yeah, it'll be 9. It is always written in, so this infix notation is special, right? It's just a syntactic convenience. At the end of the day, everything is going to be written out as functions. There are very few things in Prolog, right? It has compound terms, it has atoms, it has variables, right? So everything has to fit within that framework. This is what it's doing. So to answer Nishchit's earlier question, right? How is it evaluating addition? So Prolog knows about certain operators, right? It knows about addition, multiplication, division, less than or equal to, greater than or equal to, and so on. So these are the things that it actually understands, even though they are just function symbols. When it starts looking at an S operator and has to evaluate the right hand side, it knows about a few things. This is not an exhaustive list, but I don't think we are going to use anything beyond this, right? And that is what Prolog knows about. So these are special, right? Not every function is evaluable, but certain function symbols are known by Prolog to be numeric operators, and that's how Prolog works. So A is 20 divided by 20 gives you A is 1. Yeah, okay. So I think you can use floats. I don't know. Yeah, seems to work. I don't know the answer, frankly. Yeah, I think these are fine. So if you have a question, you can just like always play around with it and try to see if it works. We are not going to look at floats in Prolog because that's not the interesting bits of Prolog that I want to focus on. Okay. Okay. Good. So let's see. Now let's write a function that computes the length of sum of a list. So here is the fact for an empty list. It says sum of an empty list is 0 because it's an empty list. The sum of a list with head h and tail t is n if you can show that the sum of the tail of the list is m, right? Tail is m, and n, the variable that appears here, is m plus h. This is m plus h, right? This is sort of a declarative reading. We just say that is n. If you can show that sum of the tail of the list is m, and then n is m plus h. Okay. So we add two clauses, and then we can ask for the sum of 1, 2, 3. It gives us 6 back. Yeah. So as I said earlier, right? So we can there is no input and output in Prolog. It's always a query, right? So even though we use it like a function, we ask what is the sum of the list 1, 2, 3. Oops. We use this as output, but really Prolog doesn't care. Prolog is doing logical deduction, right? It's not like computing an answer. It is doing logical deduction. So you can ask questions like, what is the list X so that the sum of the list is 3, right? And for some reason I'm asking Prolog to produce just the one result. Let's see what it produces. It actually says instantiation error, right? Prolog doesn't give us what you would have liked, right? As an answer to this question, as a human, is that oh, I know that sum of a list with singleton element 3 is 3. Sum of a list with say 3 ones is 3. Sum of a list with say 1 and 2 is 3, and so on. But why is Prolog failing here, right? And for that, we can quickly look at how Prolog actually computes, right? It says instantiation error. So it must mean that there is some arithmetic issue that is happening. So in order to do this, let's trace it by hand. What I'm going to do is to go back to this and then try to connect it again. 4, 6, 7. Okay. So we're going to compute some x 3, right? This is the goal that we have, right? And then first, what we're going to do is to try the first of the clauses, right? We are trying to unify this with some, so this is what we try. This doesn't unify, right? The problem is that x unifies with empty list, that's fine, but 0 does not unify with 3. So because of that, Prolog is going to come back and say, okay, that failed. So let me try something else. So what is the second option? The second option is, let me write it down and then show you. H1 T1 N1 is sum of N1 is N1 plus H1. Okay, so this is the rule, and all I've done is I've replaced all the renamed all the variables. Okay, so x unifies with this term, right? Variable always unifies with x unifies. Oops, x unifies with this term. We know that always unifies because variable unifies with anything. So let's write it down. N1 is 3. Okay, and then let's copy the facts over to the right hand side. We know that N1 is 3, right? And we don't know anything about anything else, right? We don't know anything about these variables. We haven't specialized these variables. So now, and what Prolog does is we have 2 goals on the right hand side, right? These are the 2 goals. And SLD resolution, the way Prolog does deduction, picks the first goal that appears on the left hand side and then goes for the second one. So now Prolog is going to say, this is my goal. Let's try to satisfy that. Let's prove that goal. So Prolog is going to pick some empty list 0, right? And it turns out that it does unify, right? So empty list unifies with T1, and then M1 unifies with 0. Sorry. M1 unifies with 0. And now let's bring this result down. T1 is unified with the empty list. M1 is unified with 0. So we have a second goal. So let's transfer this information over to the second goal. So now if you look at it, we are going to use M1 equals 0, right? We don't know anything about H1. So Prolog needs to now show that this holds. I mean, what is this if you write it down, right? Let me write it down in a different color. So it says 3 is 0 plus H1, right? And just like we saw earlier, so this is not a, so it is going to look at this and then it is going to expect the right hand side to be a numeric term which doesn't have any variables. It does have this variable H1 and it doesn't know anything about how to evaluate this variable, right? So this variable H1 is the cause of the error. So here Prolog fails, right? Prolog says, okay, I don't know anything about this variable, so I'm going to stop. And this is the same thing that will happen when you do it in this Prolog interpreter. Let me quickly show it and then stop. Let me clear this up. User. I'll paste the program, right? And I'm going to turn tracing on. I'm going to ask sum of x is 3, right? And if you look at it, it's replaced this x with some variable, right? This call corresponds to this recursive call here. Both are just variables here, right? And this unifies with the first fact. right? We get this back. And if you transfer this information over, we get precisely what we had here, right? 3 is 0 plus h1. It just happened to rename the variables. So we get 3 is 0 plus underscore 9690. And if you try this, yeah. So it says arguments are not sufficiently instantiated. So that's the reason why Prolog doesn't produce what we want, right? We wanted this nice way of listing out all the results, but it produces an error, and that's the reason why we produce this error. I'll stop here. Any questions? So as you see, right? So when you ask these sort of questions, Prolog will come back with interesting answers. So unless you understand how Prolog Prolog resolution actually works, reduction actually works, it is unclear how we would have sort of figured out what is going wrong here. But if you sort of work it out, it's easy. I highly recommend doing tracing like this. And if you do tracing, these things are quite obvious. Okay. Anything else before I stop? Looks like there are no further questions. We'll continue on this in the next class. Then we'll see more examples. Thank you.